It said that last night.
It said that last night. All right, bond energies. Okay, this I purposely saved for last, and let me tell you why. Don't write these down. These are the equations you guys are used to writing for delta H, delta S, and delta G. Didn't they all look like this? Delta H, the first one we got, was delta H of the reaction equals delta H of the products minus the delta H of the reactants. And that was nice because once we got to delta S, it was also products minus reactants. And then delta G was also products minus reactants. Why did I save this guy for last? Well, you'll see in a second. Unfortunately, the formula for this guy is the exact opposite. It makes sense. I'll explain why it's opposite in a second. Because here, you're using not the energy of formation, how much energy is given off or absorbed when you form a compound, but rather the amount of energy it takes to break bonds, the amount of energy it takes to break a chemical bond. And that's why we have to use the exact opposite equation. Write down page 566 on there, by the way, because that is the page you'll find the chart you need. Okay, there's this chart on that page. Okay. Don't open to it yet, but you are going to need that in a little bit. All right, here's what I'm saying. I'm going to give you in this chart, you can look it up, and you'd be given the same chart if you were asked, or the information if you were asked on the AP exam. You're going to be given that information. How much energy it takes to break a particular bond. You're going to have to put that together, and let's see if you can figure out why the equation is the exact opposite of the equations we've been writing down for the past 2 weeks. Delta H the reactants minus delta H the products. Reactants minus products instead of products minus reactants. And that may seem confusing, because it should. It's the exact opposite of what we've been seeing. Okay? When we did delta H of the reaction using the delta H of formation information in the back of the book, it was always products minus reactants, because if you think about a compound, like H2, just use water for example, H2 plus O2 yields H2O, okay? If we do a compound like that, what I'm saying when we had to do that, remember how reason I actually used an example. I went through the whole thing, reversed some of them. Here's what I'm saying. The number you look up for this guy, and the number you look up for that guy, and the number you look up for that guy is how much energy is absorbed or released when he is formed from his constituent elements in their standard states. These guys are 0 because they are in their standard states, but this guy's not. So the amount of energy given off when this guy's formed, he's not being formed. He's being broken apart. So you have to put a negative in front of that guy and a negative in front of that guy. So the best way to do that is to put the negative in front of all the reactants. That's why there was a negative value there. Well, now I'm talking about the energies you're going to look up in this chart up here, the amount of energy it takes to break these bonds. Well, whose bonds are being broken? The reactants' bonds are being broken, so they keep their same sign. The products are the ones that are coming together, so they get the negative in front of them, changing their sign. All right? So that seems like, okay, well, all right, whatever, I'll have to memorize that. Doesn't matter. I can do that. Well, there's other problems with this, too, as you'll see with my examples. I have 2 examples to show you. Here's the first one. It would be nice if things were exactly the same, and all I had to do was, all right, so I have to remember it's reactants minus products. That's the only thing I have to worry about. No, it is not. You have something else to worry about. With this. When you use page 566, the chart on page 566, you will not be looking up the amount of energy it takes to break up a BRF3. You'll be looking up the amount of energy it takes to break a single BRF bond. How many BRF bonds are in BRF3? How many bonds are in there? Now, some people are looking at, oh, so you got to multiply by 2. I knew that. No! Yes, you do have to multiply by 2. But there's another thing about, let's draw BRF3 out. You don't have to do this right now. We'll just look. This is BR, F, F, and F. There he is. BRF3. If you look up in this chart on page 566, it tells you the energy it takes to break one BRF bond. How many BRF bonds are in BRF3? It's actually 3, 1, 2, 3, times 2. You're going to multiply by 6 for that guy. You're going to multiply by 6. So, okay, so you always multiply by the subscript, right? No. How many bonds are in a BR2 bond? Just one. I don't multiply this guy by 2. So I'm going to recommend, and what I always do if I'm doing one like this, I'm going to recommend that you draw them out first. For a guy as easy as this, it's not that big of a deal. But for the second one I'm going to do, it's a really big deal. Okay? If I draw these guys out first, BR2 is that. 3 times F2 is that. And then 2 times BRF is that. If you draw those out like I just did there, that will help you do that. Draw those out for me. That'll help you see how many bonds there really are for these guys when you go to do your equation. And let's do that equation. Delta H of the reaction equals delta H of the reactants minus the delta H of the products. Not products minus reactants because we're using bond energies. Now you need to open page 566 and learn how to use this chart because you're going to have to use it on the test. Who are you going to look up first? This guy? That's what you had to do in the past because you're doing products minus reactants, right? No, this time we're doing reactants first. So look up bromine first, and you'll see the chart is only half the chart, and you'll know why. You'll figure out why once you start to try to use it. Can you all find BR, bonds, energy? What is it? Anybody find it? Anybody find it? Did everybody find it? You're going to have to help me out because I don't have the numbers. I have the final answer, but I don't have the individual numbers. Everybody agree it's 193? 193. Do I have to multiply that by anybody? Anything? Kilojoules. Okay. It's actually kilojoules per mole, but you're multiplying by 1 mole. So 193 kilojoules per mole, but times 1 mole. All right. Plus F2. What do we have to do for that guy? 3 times the FF bond, which is what? How much? 155. 155 kilojoules per mole. You multiply 3 moles times 155 kilojoules per mole. Good. Then minus, and here you'll need brackets, although you really don't because there's only one guy, but a lot of times you do because there's 2 products. Okay? Minus, what am I going to multiply by the BRF3? BRF, I mean, 6. Because there's 2 here, times 1, 2, 3 bonds, that's 6. Times, what's the BRF actual energy? How much? 249 kilojoules. So that's 6 moles times 249 kilojoules per mole. And there you have it. Now, do the math for all that. I have the answer. Let's see if it matches. See if you get the right answer. Did you get that? Good. Good. Negative 836? All right. Excellent. So, in this case, I have to be careful. I have to use the subscripts. The subscripts don't always mean what you think they mean. So, a lot of times you get the idea that, well, if it's a 3, I'm always going to multiply by the subscript, so I'm going to multiply by 2. You don't. So then you think to yourself, well, I'll go overboard the other way. Okay? If there's a 2, I never use it. Is that correct? Let's see. If I had water as one of those guys, how many bonds, how many HO bonds are in water? 2. So I do use the 2 here. There are 2 bonds. If I had, however, just H2, how many bonds are there? 1. You see what I'm saying? Tricky. Okay, let's do one more example of a very tricky one. Check this out. Copy that all down, and I'll tell you why this guy's tricky and why you really want to draw him out. Draw him completed. Because you really would have no clue what to do if you just tried to do these guys. You have everything wrong except for probably water. Let's start drawing. You ready? C2H4. Everybody looking at that guy? Now, you have an advantage over students who are just taking an AP class and didn't have the organic you had. You should recognize C2H4 immediately as what? Ethene. Exactly. Right? You should recognize that immediately. When I go to draw this guy out, you should be able to draw him as this. I mean, we did all kinds of stuff with ethene and all kinds of alkenes. You should recognize that right away. Someone else might look at that and have no idea what to multiply by, because they didn't have the organic that you guys had. So C2H4, what do you do there? I have no idea. All right, you know. You got a double bonded here. Look at that chart when you're going to look him up. That chart you've been looking at doesn't have double bonds. Look at the chart below that chart. See the double bond for carbon? That's the one you're going to use. Don't use it yet. Let's finish these up. Here's the next mistake. Right here. I got to multiply 3 times oxygen. Well, that's okay. Oh, no. Oxygen, you may remember, also has a double bond. Remember when we drew the electron dot notations for oxygen? Okay? The correct electron dot notation for oxygen looked like that. He had to have a double bond. It's a double bond between him, like that. We're sharing 2 pairs of electrons. And so I have to multiply 3 times the oxygen's double bond, which is, again, below. Now, granted, it's been a while since we've done those, and I'm going to actually do a review of electron dot notations, hard ones, harder than this even, but certainly harder than this, where we have resonance structures and everything. I'm going to do that right before the exam. I didn't want to do all of that and confuse you in the organic part. All right? Our review of electron dot notations will show you why, again, this is like this, and why carbon dioxide is also, do you remember this? This is what carbon dioxide looked like when we did him before, too. Again, my guess is, oops, that's just 2. My guess is you probably don't remember that as well. It's been about 4 months since we did those. That was one of the first things we did. I will review that again with you. That's just 2 dots, sorry. All right, so you have to have 2 times that guy, right? Okay, and then you got 2 times whatever H2O's is O, H, H. I can't imagine that. Okay. All right. 2 times whatever water's bonds are. Now that you can see is a pain in the neck. Let's take a look over here, starting over here. What are you going to have to look up? You're going to have to look up the carbon-carbon double bond in the chart below. You're going to have to look up 4 carbon-hydrogen bonds. You're going to have to look up 3 times the 1 double bonded oxygen. 2 times 2. How many here are you going to have? 4, right? Because you got 2 of these, and there's 2 in there, so that's going to be 4 times that guy. And then you got 2 times, there's 2 more in there. What's that going to be times? 4 again. Try setting all that up and show me the numbers and the coefficients in front of them. Otherwise, I can't give you a partial credit. You have to do that. Okay? Try that now. See if you get the right answer. I do have the answer down for that. I'm going to leave out the units so that it can fit it all on the smart board, but you guys should keep your units and your coefficients. Just want to make sure you're looking up the right numbers. Look at the asterisk when you get to the carbon double bond, carbon oxygen double bond and carbon dioxide. There's an asterisk next to it. See what that means. See if you know what that means. Those are the numbers you got? If you're just copying them down, you're not getting anything out of this.
I was checking to see if they were right. I was checking. I couldn't see the first part. I was making sure I was in the first part.
Don't look at the next two. To go on your own. You're not going to make the mistakes. I can't make them for you. You got to make them. And then you'll know which ones you're going to make. That's the point of doing them on your own. I'm just putting them up here so you can check. Who got an answer for this already? Because even after you do all this, you got to keep all the coefficients straight. You got to distribute the negative. Not forget about that. So do everything that's in this bracket maybe first before you subtract it, or just change the sign of both of them. Would anybody get an answer? What do you get?
Negative 1,300.
Negative 1,300 kilojoules is what I got as well. Okay, good. By the way, you know how you looked up? There's one nice part about these that you might appreciate at least. There's obviously things that are harder about these. There's one nice thing is, when you look at that chart, are there any negative values? That chart? They're all positive, which makes sense. All right? Because what you're talking about is the energy it takes to break a bond. Every bond is going to take some amount of energy to break. He may give off more when you form the compound in the new product. Like in this case, this is a negative answer. What does that tell you about this guy? What is he? If I asked you what this guy is, endo or exothermic, what would you write? Exothermic. Negative means it's giving off energy. Okay? It's releasing energy. Okay? So this guy's exothermic. You can tell me that from this. By the way, you'll notice it'll tell you a couple of times in the homework to look these up for a particular compound. And then it will say, why isn't it exactly the same? Okay? There's a reason. There are actually a couple of reasons. There's one of the reasons in particular it's going to do is, I think it has you do the the decomposition or boiling point of water, I forget, or something like that. Boiling point of water. If I'm taking water and going from liquid water to gaseous water, why would my answer doing, actually, that doesn't break any bonds. That wouldn't be a good example. And there's some other place where it does this. It has to do with the fact that it's not at. These are average values that you look up in this chart. Okay? When you look up this chart, these are average values, and they're all taken at, the ones in the back of the book are taken at 25 degrees Celsius, or 498, or 298 Kelvin. So, you know, the ones in the back of the book, when you're doing that, now I'm thinking of where that question came over for that guy, why that one's not the same as the actual boiling point of water. You did have to do this one as a homework problem in the previous one, for the delta G one. All right, that one does not come out to be the same when you solve for T, because I meant to mention that before. Because to boil water, what are you doing? And what temperature is that happening at? 100 Celsius or 373 Kelvin. The values you use to solve delta H and delta S for that in the back of the book were at 25 degrees Celsius. So that's why that one doesn't come out to be the same. That's one of the questions that asked in your homework from last night. For this guy, the reason they're not exactly the same is similar, but not exactly the same. These are average values. For example, when you look up the carbon-hydrogen bond, this carbon-hydrogen bond will not take exactly the same amount of energy to break as it would if this were ethane or 2,2-dimethyl-4-propyl, and there was an H coming off of the middle one there. They're going to take a slightly different amount of energy to break a bond if that carbon is bound to something else besides another carbon. So they're just taking an average of those. Yeah?
Why is it 4 times 799?
Why is it 4 times 799? 2 reasons. One, I've got 2 of them here, and I've got 2 bonds here, so that's where the 4 comes from. Why is it 799? Look at the asterisk next to the carbon-oxygen bond.
Yeah, but
Okay.
so it would be 799 plus 799.
799 is 799
And then
times 2, so that's 4 times 799. It's the same thing.
That might be this one.
Yeah. So this one's 799, this one's 799, and you've got 2 of them, so 2 times 2 is 4. 4 times 7. Okay. Same reason this one. Why, if you understand why there's a 4 here, you understand why there's a 4 there. There are 2 OH bonds. Each one's 463. And I've got 2 moles of water being formed, basically. All right. Good enough.